what I'm going to do today is the Bayesian network. The difference of the Bayesian network is we really want to capture the causal relationship. Remove the assumption of independence. So now this is a probability graphic model. And if you go to read the example in the book, there's a very nice example about heartburn and heart disease. They basically based on the habit of the patient. Could be exercise and diet habit, and also the symptom. Do they have chest pain, or do they have high blood pressure? And they use that Bayesian network to detect the patient is either have heartburn or heart disease. It's a beautiful example. I don't have enough time to talk. The reason this is beautiful is the disease you want to diagnose is right in the middle of the causal chain, because it's the healthy habit for your diet and exercise causes the problem in the first place, right? That's the parent of the heartburn and or heart disease. But also you detect the symptom. The patient have a chest pain and or high pressure. That's the effect, the consequence of either heartburn or heart disease. So how do you distinguish these two? Well, in all this attribute, there's one more thing you never count. What is the one we have not counted here? The genetics, the gene. You only can statistically look at that case from the historical reason, and then based on this causal network with the probability of the historic reason, even you can trace the gene of your grandfather or something to make this diagnosis better. So that one is a really nice, beautiful example to show you how much inside information that the Bayesian network can give. That exceeded the decision tree, because the decision tree is all data, there's no links or probability. But here, the probability not only captured the information from the cause, but also the symptom, which is the consequence. Okay? So everything else is pretty much the same as the Bayesian, as a conditional probability. The human being, certainly, if you are the domain expert, you know the causal relationship. If you are in the physical science, you know which influence what, right? But how the computer know it? Computer really don't know it. The computer only can try to detect some relationship for the data, to look at the correlation, the we call it covariant matrix. That's the only thing computer do. You heard all this logic, right? About since it's rain and then the grass is wet. That's deductive, right? Okay. But the other way have been heard all often, very frequently. Oh, since the lawn is wet, it must rain. Is that true? No, that's not deductive logic. That's called objective logic. But this is how the people try to diagnose diseases, and it's called educational guess. And this lawn is wet. The raining could give a good explanation, can explain what the way the lawn is wet. But you don't have to. Mathematically, that's not right. And I write a whole book chapter about that, how people can mess up this. 95% of people can mess up that. See the difference of deductive logic and objective logic. That's very different. That's not even logic. However, there's probability. They're correlated. See, look at the reason. The grass is wet is definitely a consequence of the rain or the sprinkler system is on, right? So the grass is wet have two parents. And now you have an asymmetric relationship. If it's rain, you might set up the sprinkler system not around. Or if that's not a rain for a long time, you might not want the sprinkler system to run. There are possibility the rain in the rainy season help you set up the sprinkler system in a way that this could be the rain is a parent of the sprinkler. Human beings know that, right? But the reverse is not true. How you set up your sprinkler system would not affect the rain. Are you with me? So that, how do you computer know that? They don't know. In Weka, they don't give you those graphs though based on data, but in some other algorithm, you can input that relationship. That will be more insightful, give you better result. So look, those are the rain itself have no parents. It's the prior probability. And 20% of time rain, 80% of time it does not rain. F means false. And when you deal with the sprinkler system, you could depend on if it's rain or not rain. If it's not rain, that's 40% of time is on, 60% of time is off. And if it's raining, then the 0 time is on because you're going to turn it off, maybe. And if it's raining, then 99% of time you turn it off. Did you see it? Because you don't want to waste the water, right? That's how this link is here. Okay, make sense? And then this probability, how those come from in the data mining? They all come from examples. From maybe a community with 100 households. And they all have this frequency and you record it, and then this probability just come from the real examples. And then you get this table. It's under the condition because it has two parents. You see on the left hand, you put the two parents. The two are binary attributes. Then you have 4 different cases. Sprinkler is false, and the rain is false. So of course, you won't get a weight. Yeah, weight is false. And then if a sprinkler is false and raining, you get most of the time you get the weight is true, and 20% maybe the rain is too small. Whatever you get. That's an example. Next. How do you get this probability? When you look at the joint probability, that means the grass is wet, sprinklers are on, and that the rain is on. It's raining. It's raining. So this probability equal all the 3 products here. That's the Bayesian formula, the full version without assumption. This will give you the full version of the Bayesian formula, the conditional probability. How do you get the probability the grass is wet when it's raining? Now, grass is wet is the condition. And then you back look, it's raining. Just as I said, since the grass is wet, it must be raining. That's not 100% true, right? But there's a good probability. Are you with me? That's how we always look at the good explanation. That's how scientists discover something. Okay, now the top is raining and the grass is wet. That's the joint probability. And the bottom is the grass is wet, the probability. So the grass is wet is this G. You need to look at all the possibility that the sigma sprinklers either false or true, raining is false or true, add all those together. That's when the grass is wet. because in the diagram, it did not show you what the probability of grass is wet directly. You give all the small pieces, right? And on the top, see, what you mean is it's raining, the grass is wet, then the raining is true, the grass is wet is true, but you need to add that the sprinkling could be either on or false. In other words, another factor is a sprinkler. Either false or true, you add this two. So you're going to, I think this is usually a part of kind of a typical exam problem in the statistics class. So that's it. True, true, true means everything is true. True, false, true means the sprinkler could be false. You add these two, become the numerator. The denominator basically is all the four possibilities except that the grass is wet, always true. Can you see it? The first one is grass, G. And then you add only 36% chance, true. The grass is wet because it's raining. What's the other 64%? That means it's because the sprinkler system, right? And in here, it's a little more complicated than, look at this. The raining also affects the sprinkler system, making the things a little more complicated. What's naive Bayesian? You don't have that. You don't have that complication. Okay? Anyway, so there are all different ways to do it. Most of the time, for a very good job, if the things are like a numerical diagnosis, they typically do not have a lot of attributes because people won't get hundreds of attributes, maybe 10, 20. In that kind of application, a Bayesian network is a very good tool. Just like this, another example is diabetes example, and the heartburn, heart disease example. So create this structure. It's a very valuable information. Human beings know it. That's called the domain expertise. So in medical research, if you want to write a proposal for grant, you definitely, in the team, need one medical doctor. They have the domain expertise to know the relationship, right, between all the diseases and the symptoms. And then you determine the probability of the table. That part typically comes from the historic data because things are always repeating. And any medical data, of course, is expensive. And then you're going to use the tool, and then there's a tremendous many algorithms, but mostly based on machine learning.